Well, it means that our conception of the universe is incomplete. We have this Big Bang, but we don't know why it banged. We don't know what banged. We don't know where the bang is going. We just know there was a bang.
Yeah.
So you see, there are a lot of gaps in Einstein's theory.
The universe is thought to have popped into existence some 13.8 billion years ago, when an infinitesimal point expanded in just a fraction of a second. The Big Bang Theory has stood for the best part of 100 years after Belgian physicist Georges Lemaire first proposed it in 1927. The expansion of the universe could be traced back to a single point. However, the well-accepted model is now under the microscope after a team of researchers found a star which appears to be older than the cosmos, and that could lead to a scientific crisis. How can the universe contain stars older than itself? Is there something wrong with the estimates, or the Big Bang Theory was wrong? Join us as we dig into a star that's 200 million years older than the universe that could spark a scientific revolution. HD 140283, more colorfully called the Methuselah star, is most certainly old and is generally accepted to be one of the oldest known stars. Astronomers began observing Methuselah, named in reference to a biblical patriarch who is said to have died aged 969, making him the longest lived of all the figures in the Bible, more than 100 years ago. The curious star is located some 190 light-years away from Earth in the constellation Libra, and it rapidly journeys across the sky at 800,000 miles per hour, or 1.3 million kilometers per hour. A paper published in 2013 estimated its age to be 14.45 billion years old, with an uncertainty of plus or minus 0.8 billion years. Such a figure was rather baffling. After all, the age of the universe determined from observations of the cosmic microwave background is 13.8 billion years old. So how can a star be older than the universe? Such an unusual finding forces us to rethink what we know about the universe and generally leads to a revolution in our cosmological theories. But does it hold true? Let's analyze. First, we need to look at just how we determine the age of such a star. To understand why, first, we need to look at just how we determine the age of such a star. The progression of most stars follows a particular pattern. A protostar gravitationally collapses, which causes hydrogen to start fusing in its core, making it a proper star. The star enters what is known as the main sequence, where it spends billions of years, depending on its size, as a stable star. As it exhausts its hydrogen, it enters its final stage as a red giant or similar before ending as a supernova, white dwarf, etc. Again, depending on its size. Determining the age of a main sequence star is difficult because they don't change much during this period. There are small changes that can be observed, but they are subtle. It is similar to determining the age of a person. Someone who is 20 looks young. Someone who is 80 looks old, but someone 30 to 50 is harder to gauge because middle-aged people tend to maintain a similar look for decades. The same is true for middle-aged main sequence stars. Fortunately for astronomers, HD 140283 is not a main sequence star. It is a subgiant star, which means it has left the main sequence and is heading toward the red giant stage. That fact alone tells us it is an older star because it is beginning to enter its last stage of life. So we know for sure that it is billions of years old. Another fact we can use to help determine a star's age is what's known as metallicity. Astronomers believe that HD 140283 is old because the star has a very low metallicity. Metallicity, for astronomers, is a measure of the percentage of the chemical makeup of a star consisting of elements other than hydrogen and helium. When the cosmos began, the universe consisted nearly entirely of hydrogen, 75%, and helium, 25%, with a tiny trace of heavier elements, less than 0.01%. Those percentages reflect the mass content. When simply counting atoms, hydrogen was 92% and helium 8%. This also was the elemental composition of the earliest stars, which formed perhaps as early as 100 million years after the Big Bang. These stars, which astronomers call population 3 stars, were much heavier and brighter than the Sun, and in their hearts, stellar fusion cooked the first types of heavier elements. Population 3 stars lived only a few million years before exploding in supernovae, which blasted their heavier elements across the cosmos. The heavy elements mixed with hydrogen and helium gas, forming population 2 stars, and the process repeated itself again, with these later supernovae adding even heavier elements to the cosmos. The result was population 1 stars, which have a relatively high composition of heavier elements. Our Sun is a population 1 star. However, the Methuselah star is a population 2 star, a cosmic relic from the very birth of the universe. It has far less oxygen and iron than, for example, our Sun. Astronomers use a combination of measurements of the brightness of the star, the observed percentages of non-hydrogen and non-helium elements, and sophisticated models of stellar evolution to determine the star's age. And, as mentioned previously, in 2013, astronomers estimated an age older than the universe. So, is this a real problem? Is HD 140283 a death knell for the Big Bang? Well, it still is a puzzle because, for one, there is a pretty big difference among calculations of the star's age of Methuselah. One estimate in 2015 suggests an age of 13.7, give or take 0.7 billion years, while an estimate in 2021 suggests an even earlier age of 12, give or take 0.5 billion years. And even if the seemingly problematic 2013 estimate were 100% reliable, we need to be cautious. Most importantly, we must not just compare the point estimate for the age of the star with that of the universe, that is 14.45 versus 13.797 billion years, but we must also consider the uncertainties. The uncertainty for the estimate of the age of the Methuselah star is give or take 0.8 billion years, meaning the actual age of the star is somewhere between 13.65 and 15.25 billion years. More technically, there is a 70% chance that the actual age of the star is within that range, and a 30% chance that it is outside of it. This further means that there is a 15% chance that the actual age of HD 140283 is less than 13.65 billion years. In short, the Methuselah star's age is still unclear. Puzzled over a series of different results, some scientists decided to shift their attention to investigating the age of the universe. Surprisingly, far from being 13.8 billion years old, as estimated by the European Planck Space Telescope's detailed measurements of cosmic radiation in 2013, the universe may be as young as 11.4 billion years. If that is indeed the case, then Methuselah is once again older than the universe. The plot indeed thickens, but how accurate are these re-estimates proving to be? In fact, one of those behind the studies to date the universe is Nobel laureate Adam Rees of the Space Telescope Science Institute in Baltimore, Maryland. The conclusions are based on the idea of an expanding universe, as shown in 1929 by Edwin Hubble. This is fundamental to the Big Bang. The understanding that there was once a state of hot denseness that exploded out, stretching space. It indicates a starting point that should be measurable, but fresh findings are suggesting that the expansion rate is around 10% higher than the one suggested by Planck. Indeed, the Planck team determined that the expansion rate was 67.4 kilometers per second per megaparsec. But more recent measurements taken of the expansion rate of the universe point to values of 73 or 74. That means there is a difference between the measurement of how fast the universe is expanding today and the predictions of how fast it should be expanding based on the physics of the early universe, Rees said. It's leading to a reassessment of accepted theories while also showing there is still much to learn about dark matter and dark energy, which are thought to be behind this conundrum. A higher value for the Hubble constant indicates a short age for the universe. A constant of 67.74 kilometers per second per megaparsec would lead to an age of 13.8 billion years, whereas one of 73 or even as high as 77, as some studies have shown, would indicate a universe age no greater than 12.7 billion years. It's a mismatch that suggests, as stated, that HD 140283 could still be older than the universe. It has also since been superseded by a 2019 study published in the journal Science that proposed a Hubble constant of 82.4, suggesting that the universe's age is only 11.4 billion years. Astronomers are hoping the James Webb Space Telescope could shed light on this particular mystery. The physicist Robert Matthews of Aston University in Birmingham, UK, believes the answers lie in greater cosmological refinement. I suspect that the observational cosmologists have missed something that creates this paradox, rather than the stellar astrophysicists, he said, pointing to the measurements of the stars being perhaps more accurate. That's not because the cosmologists are in any way sloppier, but because the age determination of the universe is subject to more and arguably trickier observational and theoretical uncertainties than that of stars. But what could be making the universe potentially appear younger than this particular star? Well, according to Matthews, there are two options, and the history of science suggests that in such cases the reality is a mix of both. In this case, that would be sources of observational error that haven't been fully understood, plus some gaps in the theory of the dynamics of the universe, such as the strength of dark energy, which has been the prime driver of the cosmic expansion for many billions of years now. He suggests that the possibility that the current age paradox reflects time variation in dark energy and thus a change in the rate of acceleration, a possibility theorists have found might be compatible with ideas about the fundamental nature of gravity, such as the so-called causal set theory. New research into gravitational waves could help to resolve the paradox, Matthews said. To do this, scientists would look at the ripples in the fabric of space and time created by pairs of dead stars, rather than relying on the cosmic microwave background or the monitoring of nearby objects such as Cepheid variables and supernovae to measure the Hubble constant, the former resulting in the speed of 67 kilometers per second per megaparsec and the latter in 73. Trouble is, measuring gravitational waves is no easy task, given that they were only directly detected for the first time in 2015. But according to Stephen Feeney, an astrophysicist at the Flatiron Institute in New York, a breakthrough could be made over the next decade. The idea is to collect data from collisions between pairs of neutron stars using the visible light these events emit to figure out the speed they are moving relative to Earth. It also entails analyzing the resulting gravitational waves for an idea of distance, both of which can combine to give a measurement of the Hubble constant that should be the most accurate yet. Otherwise, it's always possible that there's something fishy that happened in the star's past that we can't know about today. It's possible that it was born as a higher mass star and something emptied off the outer layers, diminishing the star's lifetime fiercely. There might be a prevailing possibility that the star absorbed some material later in life, which altered its heavy element content, misrepresenting our perceptions today. Or it's possible that we've got a misunderstanding in the subgiant phase of the stellar evolution of these old, low metallicity stars. These unknowns are possible sources of errors when we try and compute the ages of the oldest stars. You can't have a star that exists in our universe that's older than the universe itself. Either something's wrong with our estimates for the ages of some of these stars, something's wrong with our estimates for the age of the universe, or something else that we have yet to consider. After all, the mystery of the age of HD 140283 is leading to something bigger and more scientifically complex, altering the understanding of how the universe works. The most likely explanation for the paradox are some overlooked observational effect and/or something big missing from our understanding of the dynamics of the cosmic expansion, Matthews said. Precisely what that something is sure to keep astronomers challenged for some time. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. And as always, thanks for watching, and we will see you next time.
Thinking, oh my gosh, we are seeing things better in more detail than ever before. Not only nearby, but far away.
The James Webb Space Telescope is the world's premier space science observatory. Designed with improved sensitivity and longer wavelength coverage, the $10 billion machine is expected to solve mysteries in our solar system, look beyond to distant worlds around other stars, and probe the mysterious structures and origins of our universe and our place in it. And, as expected, since becoming operational last July, the James Webb Telescope has been giving insights into the universe's distant reaches. Interestingly, using NASA's James Webb Space Telescope, astronomers even have discovered potentially universe-breaking ancient galaxies which, until now, widely accepted science said couldn't exist. 6 galaxies estimated to have been present between 500 and 700 million years following the Big Bang event 13.7 billion years ago are sending shockwaves through the scientific community. Many scientists believed that should further investigation confirm their existence, the basic rules of cosmology will need to be torn up and rewritten. Even the famous astronomer and astrophysicist Neil deGrasse Tyson also admitted that Webb's discovery could upend the current understanding of the early universe.
And so this would force it to completely rethink.
But why say that? Let's find out more in today's episode of Eyes 200M. The use of telescopes as a tool to interrogate our fundamental understanding of the universe is nothing new. Telescopes work on the basic principle of collecting and magnifying the light from distant objects to make them visible. Space telescopes, like the Hubble, which famously launched in 1990, have played a key role in pushing scientific understanding across numerous areas of astrology and cosmology. From the exploration of dark matter to determining the true age of the universe, Hubble has not only contributed to answering some of the biggest scientific questions of our time, but also revealed previously unimagined discoveries. Seemingly, the newer James Webb Telescope is determined to continue this tradition. Its improved infrared light detection technology lends it 100 times more power than Hubble, allowing novel and deeper examinations of space and the origins of the universe. As the universe continually expands, light traveling from objects in distant space towards Earth is stretched in a process known as redshift. The redder the light detected, the further it has traveled, thus, redness is a proxy for age. Utilizing these technologies, scientists have been able to re-examine regions seeing up to 13.5 billion years ago, approximately 200 million years after the Big Bang. But what have they found? A consensus-shattering discovery. In July 2022, a patch of space adjacent to the Big Dipper constellation was re-examined using the Webb telescope. According to Joel Leha, assistant professor of astrophysics at the University of Colorado and co-author of the Nature paper detailing the findings, high-resolution images obtained contained 6 blotches of extremely unusually bright and red dots. Calculations suggest these objects are 13.3 billion years away. But the age of the objects alone isn't what makes them outstanding. The measured intensity of the light detected is far larger than that emitted by a single point source, like a bright star or supernova, but is actually galactic in scale. It was initially considered a mistake, as there are numerous ways telescopes can incorrectly perceive objects. For example, gravitational lensing is a phenomenon first postulated by Einstein, detailing how light can be bent through gravitational fields as it travels through space, making it appear brighter than it is. Through investigation, gravitational lensing has been dismissed, as have other ideas explaining away the phenomenon, leaving scientists to explore one glaring explanation. The data observed is evidence supporting the existence of mature galaxies much earlier than scientific consensus can explain. In other words, the discovery would break the theory of how the early universe formed. But how? Let's analyze. Current scientific consensus holds that galaxies only began to form about 350 million years after the Big Bang. Known as dwarf galaxies, they are relatively tiny, forming through small clouds of dust, and contain up to 100 million stars. Mature galaxies like our own Milky Way, containing a minimum of 100 billion stars, were thought to take far longer to come into existence. The newest galaxies observed by the Webb telescope are proposed to contain populations of tens to 100s of billions of stars, 500 million years after the Big Bang, a time frame previously thought of as impossible. Initial indications suggest that the largest of these galaxies is comprised of mass 1 trillion times greater than that of our Sun, or 10 times that of the Milky Way. Scientists working on the data have been extremely clear about their surprise. Erica Nelson, a professor in astrophysics, said, "It's bananas," further clarifying that you just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. Despite the excitement amongst the scientific community, caution is being exercised in jumping to conclusions. That said, the implications for cosmological understanding are far-reaching. Regardless, one thing is for sure: initial understandings of 6 galaxies that shouldn't exist still play a very essential role. Either way, should findings prove to be correct, galaxy formation has been far more prolific than can currently be explained by the basic rules of cosmology. Following the Big Bang event and a period of rapid expansion, scientific models state the universe had to go through an extended period of cooling, over hundreds of millions of years, known as the Dark Age. Once conditions had cooled enough to allow gas to coalesce and collapse into the first star, it became possible for galaxies to form, but extremely slowly. The proposed theory suggests the Milky Way gives birth to approximately 2 new stars per year. However, for the aptly named universe-breaking galaxies to exist within the newly proposed time frame, they would have been forming hundreds of stars a year over hundreds of millions of years. Potentially, the Dark Age was not so dark after all, and the abundance of heavy elements such as hydrogen and helium required for mature galaxy formation was much higher than has been suggested. After all, further investigations into the 6 universe breakers are required. The researchers say it's possible some of the objects could be obscured by supermassive black holes, and that what appears to be starlight in the images could actually be gas and dust getting pulled in by their gravity. The formation and growth of black holes at these early times is really not well understood. Emma Curtis Lake, an astronomer at the University of Hertfordshire in England who was not part of the study, explains to Science News. There's not a tension with cosmology there, just new physics to be understood of how they can form and grow, and we just never had that data before. To verify their findings, the researchers could take a spectrum image of the objects they've pinpointed. This would help reveal how old they are. Galaxies from the early universe appear to us as very red-shifted, meaning the light they emitted has been stretched out on its long journey to Earth. The higher the redshift value, the more the light has been stretched, and the more distant and aged the galaxy is. With spectroscopy, scientists could determine whether their potential galaxies or high redshift candidates are as old as they appear, or if they are just intrinsically reddened galaxies from a more recent time, says Ethan Siegel, a theoretical astrophysicist who was not involved in the study, to CNET's Eric Mack. While Leha agrees that more observations are needed to confirm the findings, he notes in the statement, regardless, the amount of mass we discovered means that the known mass in stars at this period of our universe is up to 100 times greater than we had previously thought. Even if we cut the sample in half, this is still an astounding change. Astronomers are confident that the Webb telescope's near-infrared spectrograph, NIRSPEC, which surveys temperatures, mass, and chemical composition of target objects, is more than capable of providing a conclusive answer regarding their existence. In the meantime, we can all impatiently wait to hear if the current cosmological rulebook is about to be torn up, and whether our fundamental understanding of the origin of the universe itself is about to change. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. And as always, thanks for watching, and we will see you next time.